Okay, so thank you. And our next speaker is François David. We'll talk about quantum walls on random comps. Please.
Okay, so thank you for inviting me again. And so let me first say a few words about Emmanuel. Emmanuel was my first student, and you have seen that he was how promising and imaginative he was from all what he did later on. We had 12, I think, shared publications, and Bertrand, in fact, made a very good summary of what I did at the beginning of his career about the random membrane, order of membrane in biophysics and in condensed matter physics, physics of T-third polymerized membranes. So I won't present again. This was done in an excellent way by Bertrand, so thank you. And none of those publications are on random maps. Since then, I've worked on this subject, and Emmanuel, but so I want to still, at the beginning of this talk, give a small tribute to the theory of random maps that Emmanuel knows already. That's a recent research project that I've been doing, which that it went to the small town of West Montrose in countryside of Ontario, and there is a nice graveyards in West Montrose, and if you zoom on one of the graves, you found the grave of the great combinatorist William Tutt and his wife. So we should hope who is the father, maybe, of the theory of what is now called random planar maps. Okay, so now, yes. My last, I think, collaboration with Emmanuel is a paper with also Philip and Thordur Jonsson about growing tree, a process of growing trees, which for some reason was interesting for, it was associated to problem of folding of RNA. Okay, and so my last paper with Emmanuel is in fact, I think, my first paper with Thordur, and we started a very nice collaboration, which is still going on problems which have nothing to do with random maps. So I'm going to talk about a recent work still going on about quantum random walks versus classical random walks on a very simple system, which is a random comb. Rather a toy model. This I think about some quantum physics, but because we will not discuss any deep problem entanglement, as was discussed in the previous two talks, which had to deal with quantum physics by Raphael and by Charlotte. So, what is quantum walks? For just a reminder, a classical particles moving, for instance, along a line. Here you have a line. A classical particle performing just a Brownian motion, its movement is driven by a classical coin flip object. You go left or you go right. Quantum random walks motion is the particles move left or right, but it is driven by a quantum object, what people call the quantum coin flip operator, which means that in particular that if the particles goes to the left or to the right, the two states stays entangled. It's a superposition of states, no, not entangled. Okay. And therefore, in this quantum random walks problem, if you start from a particle staying at position 0, the classical random walks, in fact, is just a Gaussian diffusion, while the quantum process, the wave function, this is the square of the wave function, the probability, as peaks are quantum oscillation, and it moves rather like a ballistic rather than a quantum diffusion problem. Okay. So the simplest quantum random walks is the quantum coin flip operator is just an identity system. And therefore, you just have to solve the continuous time Schrödinger equation on this object. But it already captures some feature of the full quantum random walk process. So basically, I'm doing first year quantum mechanics, but on an object which displays some interesting feature, which is a random comb. So what is a comb? A comb is an infinite comb is just a very simple system where you have a line, a discrete line Z, which we call the spine, and then you have a half line, which are the teeth of the comb. And if you have a regular comb, and if you start from a single point here at the origin and perform a classical random walks, so a diffusive process, some interesting feature appears. First, along each teeth, the diffusion takes place as a classical diffusion random walks on a half line. So the average distance to the point after time t grows like the square root of t, which is related to this fact that the spectral dimension of the Laplacian operator is 2 for the process. But along the spine, the diffusion is slower. The diffusion is slower, and it diffuses with the power t to the power 1/4, which is not completely trivial. It's not easy to. Okay, but that's for classical diffusion. So, in fact, with Thorder, we started a few years ago to look at what's the quantum walk on this comb, which is an interesting process. So the question is, how does a particle starting from a point on the spine diffuses, but according to the law of quantum mechanics? Okay, and we found something non-completely trivial, which is that the particle diffuses so this represents the density of the wave function. Basically, it's a crude drawing. So part of the wave functions of the particle escapes with some velocity, so it's like a ballistic regime along the teeth, and part of the wave function stays confined near the spine and propagates also ballistically, but along the spine with another velocity. So you have a velocity associated to the spine and a velocity associated to the teeth. Okay. But that's so we did a lot of studies, a lot of interesting math to do to look at the asymptotics of this regime, whether they are scaling regime for the wave function. You use some nice, easygoing resurgence theory, some semi-classical analysis. Okay, but that's what we did in this paper. Now, what about introducing some randomness? So we start to introduce some random geometry, but very simple random geometry. So introduce some geometric disorder. Just take a random comb where with some probability, I see there were some equations and they are not appearing, okay? Some teeth are removed. I'm start to be worried because maybe so you have the same problem. You start from a point, the particle diffuses along this subject, but some teeth are missing. I start to be worried. Ah, my God, help! The equations have disappeared. We checked the first slides where there were no equation. Yes. I'm very sorry.
Maybe we take the previous.
Pardon?
The first.
I'm very sorry.
Maybe we can take this one.
Yes, try a different one. Oh, it's a disaster. That's strange. Ah. No equation. can you start from this tablet, which has the equations?
C'est un iPad.
iPad.
On peut faire un airdrop en PDF.
What?
Un airdrop en PDF.
Ah, mais c'est pas le PDF.
On peut l'exporter.
Sur ça, non. J'ai le PDF, mais sur mon...
J'ai pas vraiment de solution du coup.
Ah, well, sorry. Maybe. Tu peux pas juste reporter l'écran?
Non. Ah, peut-être. Ah ouais, mais il me faut le Wi-Fi. Et si je mets le Wi-Fi, je coupe le réseau là.
Ok, attends. Sorry.
Je peux pas faire ça.
Non.
Et on peut pas l'exporter.
Ben, je sais pas.
Partager.
Well, maybe we should just make a...
Exporter. Non.
Ben non.
Je peux pas. Exporter PDF. Ok.
Tout.
Exporter. Et partager en airdrop. 2 secondes.
Est-ce que tu me vois?
Pas encore.
Ah, présentation bloc.
Ok. Accept and open. Ok.
Oh, this is strange. Okay, so yes, okay, thank you. So, okay, so that's where I was. So we consider now this random comb, and of course, this is a probability where we just have some probability p to have a hole, namely a tooth missing. So the main parameter is just the probability to have holes along this comb, so missing tooth. So to solve the problem, it's just elementary quantum mechanics. So we look for the energy eigenstates of the Hamiltonian. So we have some wave function phi, where n is, n is going to, oops, I'm sorry, n is going to denote the position of the teeth on the spine, and j is the position along the tooth. So you have a wave function associated to each point on the tooth, and you have some equation, some wave equation with the energy parameter E, and you have two kinds of states. For states with energy between 0 and 4, the energy parameter is parameterized by an angle theta, and you have just plane waves propagating along the teeth with a phase plus Ig or minus Ig, which corresponds to incoming and outgoing waves. We'll discuss that. And if the energy is larger than 4, then you have eigenstates which are exponentially decreasing along the tooth with a factor exponential minus some sigma j, and the relation between sigma is E, the energy is 2 plus 2 cosine, hyperbolic cosine of theta. So the states with energy larger than 4 are just localized near the spine, exponentially decaying along the teeth, while the energy state with energy less than 4 propagates along the teeth, so that the B's here with this phase correspond to in states going along down along the teeth, and the A amplitudes correspond to outgoing states getting out of the teeth up. Okay, and you have some eigenstate equation along the spines for those coefficients A and B for states on teeth, and coefficient C for if n is a whole. You can define that an plus bn equals cn if you are on a whole, and therefore you have wave equation, which is very simple, relating the amplitude, the coefficient A, B, and C along the T's, which take this form for energy states less than 1. This form if the site n is a tooth, and this form, slightly simpler, if the state is a whole. And for the energy larger than 4, they take this form with sigma instead of E I theta and E minus I theta, and here. Okay. Oh. Okay. So those are very simple equations, and in fact those equations, in fact, can be looks very, very similar to the equation where you take a single line and you have a wave function psi associated to each side on the integral line with so this is a hopping parameter, this is the energy, and you have a random potential on each side, V of n, where V of n is 0 or some constant V, according to some identical independently distributed distribution on each side, which is a very simple prototypal model of disordered conductor, which was introduced by Anderson and which is related to a famous problem of random harmonic chains introduced by Dyson and Schmidt in the beginning of the 60s. So it's a very, very old problem and a prototypical problem. And this is very interesting because that's the toy model, the Ising model of phenomenon of Anderson localization. So here, for instance, what I show on this picture is you take a chain of length 20, very small. You take probability 1/2 and 1/2 to have potential on each side 0 or V. And here I plot the value of V. So when I change the value of the potential, of the disordered potential, and here this is the energy, and these are the spectral flow. So each point represents the energy eigenstate for some eigenstate, and this is how the energy vary with the disordered potential. So for V equals 0 here, this is just the ordinary regular chain. And you see that when you have some disorder, the eigenstate, the energy eigenstates, and for V large enough, you have 2 bands of states. And the phenomenon of Anderson localization is that when this is random, then the typical eigenstate decays with the distance exponentially. And this chi of E is just called the localization length. It says that the energy eigenstates are localized in space, and this chi is the inverse of a Lyapunov exponent, which is associated to a random dynamical process, a Riccati equation, or to the formulation of this problem in terms of product of random matrices. So since the 60s, and this has been developed until now, there are lots of mathematical results based on, for instance, a theorem by Furstenberg, by a method of Schmidt, Herbert, Jones, Saules, and by numerical study, which comes from localization theory. So what we did was simply to apply this to this problem after some time. So I just present very quickly some results what we got. I could give a lot of theorem, well, some theorem and discuss, but I just want to give an idea of what the kind of problem we are looking at. So first, if you look at the energy eigenstates which are localized along the spine, so which have energy larger than 4, we can show that the number of such states normalized by the length of the comb is in fact a random variable. It depends on the randomness, but as the length of the cone becomes infinite, it converges almost surely to a constant which depends only on the probability to have holes. Okay? The second result is that those, for a given P of probability for holes, all the energy eigenstates with energy larger than 4 are localized, and you can measure the Lyapunov, compute the Lyapunov exponent. For instance, this is the Lyapunov exponent for P equal 1/2 as a function of the energy, and it has these typical curves, which in fact it's a fractal curve with a dense number of singularities, but it's a continuous. and it has a minimal. So you see that the Lyapunov exponent is always positive, which means that the localization length is always positive, and it has an upper bound. What's another interesting phenomenon is that now I look for the minimal value for the Lyapunov exponent. Here it's somewhere here. And I look at how the minimal value of the Lyapunov exponent, so the maximal value for the correlation length, vary with the probability to have holes. And it, in fact, somehow smooth curves. It starts linearly with the probability of holes. And at some point, there is a change of regime where you have mostly holes. So when P is larger than 0.8, and then it drops down to 0 again for simple reason. So localization is very strong for such states. Okay. For the energy eigenstates less than 1, we have seen that those states depends on are parameterized by two coefficients for a given energy labeled by theta. And so the B states correspond to in states, red states. A coefficient corresponds to out state, and one question is, for instance, you get the particles incoming with a fixed energy along a definite tooth. How is it diffused by the comb, and what's the shape of the reflected wave function? So this is just S matrix. So there is an S matrix which gives what are the A coefficient out of the initial B coefficient, and we can study the localization for the structure of this S matrix, namely you start from a given incoming wave along a teeth. Is the reflected wave exponentially decaying and localized? Or you can also look at what are the eigenstate of the S matrix also localized. Namely, the eigenstate are labeled by a phase shift. Okay. And here I'm showing, for instance, what is the Lyapunov, two curves, numerical curves, how the Lyapunov exponent for those reflected states vary with the probability of holes, and you see that except near when the energy is 0, the localization length is finite. And now for the eigenstates of the S matrix, the Lyapunov exponent, in fact, is usually positive, but there is some value of the phase shift here where it's small. It vanishes for some reason. So it's not completely trivial what's going on. But we have, for this, we can have also an equal result. Okay, so now let's go back to the initial problem. We have a particle which stays at initial time at a given point on the spine, at position n0. We let it evolve quantum mechanically, and after a long time, in fact, from that you can see that you have part of the wave function stays close to the spine, that's represented by this band, and part of it escapes along the teeth. And you may ask, what is the total probability starting from n0 to stay near the spine at infinite time? That's called P-log of n0. You can also say, among this, what is the probability to a particle to stay near the spine but to be localized a bit along, the first point on the teeth at situation n. So that's a 2-point function, which is the probability, the quantum probability to be localized near the spines at the teeth n, starting from n0. And of course, you may also ask, what is the probability to escape to infinity at large time along a tooth n, starting from n0? So for a random comb, all those probabilities are, quantum probability, are random variables. It depends on the disorder of the comb. So we have to study what's their law. Do they converge in law? Do they converge in almost surely to some number? And for that, we have some numerical estimates, and we have some analytical hints. So first, this is, for instance, a curve which shows what is the probability to escape as a function of the probability of holes. And the probability, this probability, so this is total quantum probability, decreases with the number, it's a probability to stay. So it decreases with the probability of holes from 0 to 1. Okay, so that's typical results we are looking at. Now there are some interesting questions, and I add this is my last slides. From these numerical studies we are performing at the moment, we have some interesting questions. First, this is a numerical guess. We look the probability to stay localized along the spine starting from a point on 0 is a random variable. So this is a typical plot of the probability distribution of this quantum probability P naught. Okay. Average over some large number of comb of average over the initial position. That's the same. And it has a gap. The probability to stay localized is small, so this is an histogram. This is the probability to stay localized depending on the point you start from, n0 on a random comb. And it has typically two support, so it has a gap in the probability. Either it's something of order 0.4 or the probability is much smaller to stay along the comb. And experimentally, you can, in fact, if you start from a point n0, which is a tooth, the probability is low. If you start from a point which is a hole, the probability is higher, and there are some physical reasons for that, but they are clearly separated. So there is a gap, and it will be interesting to understand whether this gap is a real gap or whether there are some exponential tails that we cannot see in those numerical simulation. Okay, so that's something interesting. Also, we can show that the probability, if you start from a point n0, and after a long time, you look at the probability to stay localized at a site n, and you take this time average of this because that's easier to compute, you find that this two-point function decays exponentially between the distance between n0 and n. Therefore, this is a phenomenon of localization which shows that the disorder is relevant. So how can we prove that and understand exactly how it goes? This is rather easy to understand. This should be harder. So disorder is relevant for the part of the wave function which stays localized to the spine, on the spine. Now, what is the probability to escape at infinity? There is a part of the wave function which gives some probability for the particle to escape along the tooth. So what's the probability to escape at infinity along a tooth at position n, starting from an initial point at point n0? That's the probability to escape starting from n0 along the tooth n. And we find that, well, we expect that it should decay with the distance, but not exponentially, but as the distance between the initial point and the tooth with the power -4. And that's something which is proven for the regular comb with no holes, but we have an analytical guess that this is also true with a different coefficient when you take the expectation value of this, the expectation of this probability, when the probability to have holes is non-zero. So for this question, what is the probability to escape? The disorder is irrelevant. Well, this is a curve which shows this localization for this phenomenon, so we have no curves on that. So there are still regimes. For some quantities, the disorder is strongly relevant, as expected from the theory of localization, but on this random comb, for some question, like this one, the disorder is in fact irrelevant because you have the same scaling law for the regular comb with no hole and for the random comb with the probability to have holes. So that's work in progress. That's definitely a quantum process, and we hope that leads to interesting questions for other models. So I'm going to thank you for your attention, and Emmanuel, joyeux anniversaire, continue sur ta lancée. And this is one of the only pictures I have from Emmanuel when we were both younger, and I let you guess where this picture was taken. Okay, so thank you very much, and thank you, Emmanuel.
Thank you.
So we save.
Are there questions?
Where was the picture taken?
What?
Where were the pictures? I have some idea, but
What?
where were the pictures taken?
It was, I think, taken
Israel?
in Ein Gedi, so on the Black Sea or
Yes, that's
Salt
what- okay,
Sea or
that's what
whatever.
that-
So
so
I don't remember if this is in
Yeah.
Israel or Palestine, but it is in the
Yeah,
Middle
the Black
East.
Sea. Okay, that was my guess actually.
Yes.
Okay.
Thank you. Any other questions? Okay, so then let's go for coffee break. Thank you.
Okay. Thank you.